The example of DAMD, as noted above, DAMD differs from AMD in two respects. The additional ways in which the agents can influence the outcome referred to hereafter as computational manipulation, and the measure of computational complexity, the aforementioned network complexity. Here, we briefly discuss two examples of DAMD that illustrate these issues. The first is the distributed implementation of a VCG mechanism. See Chapter 9. We will ignore network complexity in this example and focus on how to prevent the manipulation of the computation. The second example is sharing the cost of a multicast transmission. It illustrates the notion of network complexity, but because we assume the presence of a trusted computational infrastructure does not involve computational manipulation. Distributed implementation of VCG. We now discuss one way a set of agents can jointly implement a VCG mechanism without fear of manipulation. We start with a set of outcomes O and a collection of agents N, each with his own valuation Vi over those outcomes. In our notation, O wave is an outcome that maximizes the total social welfare of the agents. That is, O wave equals to the argument of the maxima of the summations of Vi of O, summing for all index I in N, and where the maxima is taken among all little o in big O. W is the maximum total social welfare value, and the W minus I denotes the maximum total social welfare value of all agents except the ith. For convenience, we focus on the particular mechanism in which Pi equals to W minus I minus W plus Vi of O wave, where Pi is the payment by agent I. We assume that there is no trusted center, i.e. that the computation of the VCG mechanism must be done by the agents themselves. However, we do presume the existence of some central enforcer without whose responsibility it is to implement the outcome O wave decided upon by the agents and collect the payments. The enforcer can impose severe penalties if the agents do not agree on an outcome. To see how a distributed computation can be manipulated, consider a network in which the nodes are connected in a ring, and there is exactly one agent at each node. Assume that the agents are computing a second price auction of a single good by passing around a message containing the top two bits for that good. If an agent puts his bid on top and puts in a very low bid for the second bid, then he can get the good more cheaply, as long as these fields are not overwritten by some later agents that have higher bids. More generally, consider any distributed algorithm A capable of running over an arbitrary number of computational nodes that takes as input a set of agent evaluations and produces the maximizing outcome and the payment. As the preceding example suggests, if we run A over any subset of N to compute O wave W and each W minus I, then there is the possibility that an agent can manipulate the computation. One way to avoid this is replication. Break the agents into two groups, have them exchange all their valuations, and then have each group compute its own version of O wave and the PI. If the two groups agree on the outcomes and payments, then those outcomes and payments are adopted. If not, all agents suffer a severe penalty. Here, an agent plays different roles in the two versions of the computation. In the first, his role is to help compute the outcome and the payments. In the other, his role is to provide his valuation so that others may perform this computation. For the first version, an agent I could engage in arbitrary computational manipulation in an attempt to obtain a more favorable PI for choose an outcome he prefers to the socially optimal one. In the second version, all he could do is lie above VI. Because the VCG mechanism is strategy-proof, the agent will reveal truthfully to the other computational group, and therefore, to avoid a severe penalty for inconsistency, will carry out the computation faithfully. Notice that faithful computation is not a dominant strategy. If, for instance, all the other agents decide to choose a suboptimal outcome, then agent I is better off going along with that choice rather than causing a disagreement and triggering the severe penalty. However, if all the other agents faithfully execute the prescribed algorithm A, then agent I is best off doing so as well. Thus, the most natural solution concept when considering computational manipulation is not dominant strategies but instead ex post Nash equilibrium, which was defined in Chapter 9. We will expand on this point further when we discuss interdomain routing in section 14.3 below. In this example, we have focused on computational manipulation and ignored network complexity. In our next example, we do the opposite.